Before we get into this one, if you enjoy these deep dives into science and reality, a quick like or subscribe goes a long way. It is a small thing on your end, but it genuinely helps this channel keep going. Now, let's begin. Right now, in a laboratory in California, there is a machine that has to be kept colder than the space between galaxies, not for safety, not for power, not because it runs on some exotic fuel. It has to be that cold because if the temperature rises even slightly, the universe itself starts interacting with it, and the moment that happens, the machine stops working. Most people think of quantum computers as very fast calculators, bigger, stranger, more expensive computers that will one day crack passwords and simulate drugs. That picture is not wrong, but it misses the part that physicists find genuinely unsettling. To build a quantum computer, you have to take a position on one of the deepest unsolved questions in all of science. What does reality actually do when nobody's watching? Engineers who build these machines have had to make that question physical, practical. They had to build rooms and chambers and shielding systems and cooling towers, all to manage what happens when the quantum world meets everything else. You will see why a particle in two places at once stops being in two places the moment anything in the environment finds out about it, and why that single fact is the same puzzle Einstein and Niels Bohr argued about for 30 years. You will meet the physicist who turned that argument into a test, and the three scientists who spent decades running that test until the result could not be denied. And you will watch what happened in December 2024, when a 105-qubit processor named Willow did something that led its own creator to say the computation may have happened across parallel universes. That claim is contested. The machine is real. And the strangeness underneath both of them is older than computing and stranger than most people realize. We begin. Let me tell you what is actually inside a quantum computer. Not the sleek white exterior you have seen in photographs, not the cloud infrastructure or the cooling system, the thing at the center, the part the whole machine exists to protect. It is a small chip, roughly the size of a postage stamp. It contains anywhere from a few dozen to a few hundred tiny loops of superconducting wire. Each loop is a qubit, and a qubit is not like anything else in computing. A normal computer bit is either 0 or 1, always. At every moment it has a state, and that state is definite. A 0 is a 0, a 1 is a 1. The whole history of computing is built on that simple fact. A qubit is different. Before it interacts with anything else, before the environment gets involved, a qubit exists in what physicists call a superposition. It is not 0. It is not 1. It is, in a very precise mathematical sense, a combination of both at the same time, weighted by probabilities that can be tuned and manipulated. I want you to picture that carefully because it is easy to hear it and let it slide by. Imagine you flip a coin and catch it under your palm without looking. In ordinary life, the coin is either heads or tails. You just do not know which. That is a classical bit. It has a definite state. Your ignorance is your problem, not the coin's. A qubit is not like that coin. A qubit before measurement does not have a definite state. The mathematics describes it as genuinely existing across multiple possibilities at once. The ambiguity is not in your ignorance, it is in the thing itself, and that is exactly what makes quantum computers powerful. When you run a calculation on a qubit in superposition, you are, in a real sense, computing across multiple possibilities simultaneously. String together hundreds of entangled qubits, and the number of simultaneous states grows exponentially. 2 qubits, 4 states. 10 qubits, over 1,000 states. 300 qubits, more states than there are atoms in the observable universe. Here is the problem. That superposition is extraordinarily fragile. A single stray photon of light, a tiny vibration from a passing truck, a fluctuation in the electromagnetic field from a distant power line, any uncontrolled interaction with the environment and the superposition is lost. The qubit becomes effectively classical. It has a definite value. The quantum calculation is ruined. And the output you get is garbage. To prevent this, engineers have to build the most thermally isolated environments ever created by human beings. Google's quantum processors operate at 20 millikelvin. That is 20,000ths of a degree above absolute zero. The temperature of deep space, the void between galaxies, is about 2.7 Kelvin. The inside of a quantum computer is roughly 135 times colder than that. The cooling is only part of the problem. Engineers also measure two separate timescales for how long a qubit can survive. The first is called T1, the relaxation time. How long before the qubit spontaneously loses energy to the environment and falls from its excited state to its ground state, destroying the quantum information. The second is T2, the dephasing time. How long before the delicate phase relationship inside the superposition gets scrambled by environmental noise? T2 is often shorter than T1 because phase can be disrupted even without the qubit losing energy. On Willow, Google measured an average T1 of around 100 microseconds, 5 times better than their previous chip, an achievement that required years of materials research, improved fabrication techniques, and careful management of every surface, wire, and joint in the cooling system that might carry noise to the chip. 100 microseconds, less time than it takes you to blink. That is the window the universe allows before it reasserts itself. Think about that for a moment. We have built a machine that requires conditions colder than the cosmic background radiation of the universe, just to function for less than a millisecond before the world disrupts it. That is not an engineering footnote, that is the first clue. Because the question of why the qubit loses its superposition and what it means for it to lose it is not just an engineering headache. It is one of the oldest and most unresolved questions in physics, and it has a name, the measurement problem. But to understand that problem properly, we need to go back to an experiment that has been confusing physicists for almost a century. An experiment so simple that it can be described in 2 sentences. Yeah, and so strange that those 2 sentences have generated an argument that has never been fully resolved. Take a beam of light and aim it at a barrier with 2 narrow slits cut into it. Behind the barrier, place a screen. What pattern appears on the screen? If light behaved like particles, like tiny bullets, you would expect 2 bright lines on the screen, 1 line from each slit. Simple. Obvious. What particles do. But that is not what happens. What appears on the screen is an interference pattern, a series of alternating bright and dark bands, like ripples in a pond crossing each other. This only happens when waves interact. When the peak of one wave meets the peak of another, they add together and make a brighter band. When a peak meets a trough, they cancel and make a dark band. Light, in the double-slit experiment, behaves like a wave. That part is old news, but here is where it gets strange. Physicists ran the same experiment with electrons. Individual electrons, fired one at a time at the barrier. They waited, and over thousands of individual electron impacts, a pattern built up on the screen. And that pattern was an interference pattern, the same alternating bands. But how? Each electron went through the barrier alone. There was no other electron to interfere with. Each one should have gone through one slit or the other and left a single dot somewhere behind it. When scientists tried to find out which slit each electron actually went through, by placing a detector at the slits, something remarkable happened. The interference pattern vanished. The electrons started behaving like particles again, 2 piles of dots, one behind each slit. The act of looking, or the act of measurement, changed what the electron did. Let me say that again because it is the thing that matters here. When nobody was watching which slit the electron went through, it behaved as though it went through both. It existed in a superposition of two paths simultaneously, and those two paths interfered with each other. When somebody looked, when a detector recorded which slit the electron used, the superposition was gone. The electron chose one path, and the interference disappeared. This is not a quirk of experimental design. It is not a limitation of our instruments. Physicists have run this experiment in hundreds of variations, with electrons, atoms, molecules, and even complex structures made of hundreds of atoms. In 1999, a team in Vienna led by Anton Zeilinger demonstrated interference with Buckminster fullerene molecules, each one a cage of 60 carbon atoms, large enough to see in an electron microscope. The interference pattern appeared. The molecules were behaving like waves. The result is always the same. The quantum world and the act of measurement are entangled with each other in a way that our ordinary picture of reality cannot accommodate. Let me say what this means physically, because it is easy for it to sound like a trick. Before measurement, the electron does not have a position at the slits. It has a wave function that spreads through both slits and interferes with itself on the other side. The interference pattern on the screen is not caused by many electrons influencing each other. It is caused by each individual electron's wave function travelling through both paths simultaneously and producing a probability pattern on the screen. Your intuition wants to say, surely the electron went through one slit, we just do not know which. But that is wrong. If it had gone through one slit, there would be no interference pattern. The interference is proof that both paths were taken, in some mathematical sense, simultaneously. The moment a detector records which slit the electron used, the interference vanishes, not because the detector disturbed the electron mechanically, because the detector's record of which path was taken is enough to destroy the superposition. Information, not force. Knowledge, not disturbance. That is what collapses the pattern. And this is the thing that has been sitting at the centre of quantum mechanics for 100 years. Not a technical puzzle, a conceptual one. A question about what information and observation mean at the level of reality's foundations. A particle is in a superposition until something in the environment interacts with it and carries away information about its state. Then the superposition is effectively gone. The particle has a definite property. But where did the superposition go? What exactly happened? And why does the carrying away of information make such a fundamental difference? These are not rhetorical questions. They are the questions physicists have been trying to answer since the 1920s, and they are the same questions a quantum computer engineer faces every morning when they check how long their qubits held their coherence overnight. Here is what makes the measurement problem so strange at its core. Physicists have an equation that describes quantum systems perfectly. The Schrödinger equation, written down by the Austrian physicist Erwin Schrödinger in 1926, tells you exactly how a quantum state evolves over time. Feed it the state of a qubit right now, and it tells you, with mathematical precision, what the state will be a second from now, an hour from now, a year from now. It is one of the most precisely tested equations in the history of science. Every prediction it makes has been confirmed experimentally. It works. But here is what the Schrödinger equation does not do. It does not describe measurement. When you measure a qubit, you do not get a superposition. You get a single outcome, 0 or 1. The superposition is gone. But the Schrödinger equation, applied to the qubit and everything that interacts with it during measurement, keeps running smoothly. It keeps producing a wave function that contains all the possible outcomes. It never picks one. It never collapses. Let me put that more concretely. Imagine you have a qubit in a superposition of 0 and 1. You bring a detector into contact with it. The detector is itself a physical system made of atoms governed by quantum mechanics. According to the Schrödinger equation, the qubit and the detector become entangled. Now the total system is in a superposition of two states, qubit 0 with detector reading 0 and qubit 1 with detector reading 1. Both branches are still present in the wave function. The equation has not picked one. Now the detector interacts with the wire that carries its signal, which interacts with the amplifier, which interacts with the display, which interacts with the air in the room, which interacts with the person looking at it. At every step, the Schrödinger equation just keeps entangling everything together. The wave function of the entire system, qubit plus detector plus room plus physicist, keeps expanding. It never collapses. It never picks. And yet the physicist sees one outcome. That gap between the smooth universal wave function that never picks and the definite experience of one outcome that every physicist has is the measurement problem in its most precise form. There is a separate rule called the Born rule that tells you the probabilities of different outcomes when you measure. If the qubit's wave function says 70% probability of 0 and 30% probability of 1, the Born rule tells you that you will get 0 70% of the time and 1 30% of the time. It works. Every experiment confirms it, but the Born rule is an addition to the theory. It is not derived from the Schrödinger equation. It is accepted because it works, not because we understand why it works from first principles. Physicists call this the measurement problem, but it is actually three separate questions sitting inside one name. The first is the problem of outcomes. Why does measurement give one definite result, and not a blurry mixture of all the possible results? The Schrödinger equation gives you a smooth superposition. Measurement gives you a sharp answer. What bridges them? The second is the problem of preferred basis. When a measurement happens, why does the outcome come in the form of position, or spin, or polarization, and not in some other strange quantum combination? What decides which properties become definite when we look? The third is the problem of where the boundary is. How big does a system have to be before it stops behaving quantum mechanically? Is there a size or a mass or a complexity beyond which superpositions cannot survive? Or is the boundary something else entirely? These three questions have been sitting at the centre of physics for nearly 100 years. Brilliant people have tried to answer them, and the answers they have reached, as we will see, are not comfortable ones. But first, a different question. One that was burning at the centre of physics long before quantum computers existed. A question about whether any of this strangeness was actually necessary. Because Einstein did not think it was. In 1927, at a conference in Brussels called the Solvay Conference, the greatest physicist in the world gathered to argue about what quantum mechanics actually meant. The mathematics was not in dispute. Quantum mechanics worked. Its predictions were astonishing in their accuracy. Everyone agreed on the numbers. What they could not agree on was what the numbers described. Albert Einstein's position was, in simple terms, that particles have definite properties before you measure them. A particle has a definite position, a definite momentum, a definite spin. You just do not know what those properties are until you measure them. The uncertainty in quantum mechanics, Einstein believed, was a sign that the theory was incomplete, not that reality itself was fuzzy. There should be hidden variables underneath, deeper facts about the particle's state that a better theory would one day reveal. Niels Bohr's position was almost the opposite. The wave function, the mathematical object that quantum mechanics uses to describe a particle, is all there is. Asking what the particle's state is before you measure it is not a meaningful question. Reality does not have definite properties until they are observed. Measurement does not reveal a pre-existing state. In the Copenhagen view, measurement creates the observed outcome. Einstein hated this. He spent the last decades of his life trying to show that Bohr was wrong. In 1935, he wrote a famous paper with Boris Podolsky and Nathan Rosen, now known as the EPR paper, pointing out a consequence of quantum mechanics that seemed to Einstein to prove the theory was incomplete. The argument went like this: imagine two particles that interact and then fly apart. Quantum mechanics says their states are entangled. Measure the spin of one particle along a certain axis, and you instantly know what the spin of the other particle will be when measured along the same axis, no matter how far away it is. Einstein said, this is only possible in one of two ways. Either there is some faster-than-light signal travelling between the particles, which violates relativity, or the particles had definite spin values all along, set when they interacted and carried with them as they flew apart, and measurement simply reveals those pre-existing values. Relativity was not going to break, so the particles must have carried the information with them, hidden variables, local realism. Bohr disagreed. He said the particles did not have definite spins before measurement. They had a shared quantum state. Measuring one made the outcome of measuring the other determinate, not by any signal travelling between them, just by the structure of quantum mechanics itself. The argument was philosophical as long as both sides made the same predictions. And for 30 years they did. Then, in 1964, a physicist named John Bell changed everything. John Bell was a theoretical physicist at CERN. He was Irish, quiet, and deeply uncomfortable with the fact that the most successful theory in the history of physics came with no agreed-upon account of what it actually described. He thought about the EPR paper, he thought about hidden variables, and he realised something that nobody had seen before. If Einstein was right, if particles carry hidden variables that determine their measurement outcomes in advance, then those outcomes, across many experiments on many entangled pairs, would have to obey certain statistical limits. Here is why. Imagine two entangled particles flying apart to two distant detectors. Each detector can be set to measure spin in different directions. If hidden variables carry the outcome information with them, then the correlations between the two detectors' results are limited by the fact that the information had to be packed into the particles at the moment they interacted. The particles cannot know in advance which direction the detectors will be set to, so their hidden variables can only give them preset answers to a finite number of possible questions, and that places a mathematical bound on how correlated the two detectors' results can be. Bell worked out that bound precisely, and wrote it down as an inequality. If local hidden variables exist, the inequality holds, always. Then he showed that quantum mechanics predicts correlations that would violate that bound. Here is the key point. Bell was not arguing that quantum mechanics was wrong. He was showing that if quantum mechanics was right, then the kind of reality Einstein imagined, where particles carry definite properties that travel with them and determine outcomes locally, could not exist. The two things were logically incompatible, and now there was a test to decide between them. Run the experiment, measure the correlations. If they stay within Bell's bound, Einstein wins. If they violate Bell's bound, local hidden variables are ruled out. Reality is stranger than Einstein needed it to be. Bell published his theorem in 1964. It was a masterpiece of clarity in a paper that almost nobody read for years. It was too philosophical for most experimentalists, too concrete for most theorists. Bell himself went back to work on accelerator physics. But a few people read it. And before we get to the experiments, it is worth spending a moment with what Bell's inequality actually says in plain language, because it is one of the most remarkable logical arguments in the history of science. Here is a simplified version. Imagine two detectors, each able to measure a particle's property in one of three settings. Call them A, B, and C. For each pair of entangled particles, one goes to each detector. The operators can choose which setting to use for each measurement. If the particles carry hidden variables, definite preset answers to all three possible questions, then there is a mathematical limit on how often the two detectors can agree when they are set to different settings. Bell worked out this limit. For any local hidden variable theory, the correlation between the two detectors' results, across many measurement pairs at different settings, cannot exceed a certain value. Quantum mechanics predicts that for entangled particles, the correlation will exceed that value, not by a little, significantly. So the test is precise. Run many pairs of entangled particles through the detectors with randomly chosen settings. Calculate the correlation. If it stays within Bell's bound, hidden variables survive. If it exceeds Bell's bound, hidden variables are ruled out and quantum mechanics wins. The elegance is in the precision. Bell had taken a question that looked philosophical and made it into a number. Either the number is above the bound or it is not. Either the universe is locally real or it is not. And one experiment properly designed could decide. But a few people read it, and one of them decided to build the apparatus. John Clauser was a graduate student at Columbia University in the late 1960s when he came across Bell's paper. By his own account, he could not stop thinking about it. He became obsessed with a question most of his colleagues considered already settled. What is quantum mechanics actually saying about reality? Clauser wanted to run the experiment. His supervisors were skeptical. Bell tests were not fashionable physics. They were too foundational, too philosophical. The consensus was that quantum mechanics worked and the interpretation could wait. But Clauser pressed on. He found a collaborator, Stuart Friedman, and together they built an apparatus that produced pairs of entangled photons and measured their polarizations at different angles. The experiment took years to design and run. In 1972, they published their results. Bell's inequality was violated. The correlations between the entangled photons were stronger than any local hidden variable theory could explain. The result agreed with quantum mechanics. Einstein's picture of a locally real universe had its first experimental crack. But there were loopholes. The detectors were not efficient enough to catch every photon. Maybe, some argued, the photons that were missed would have behaved differently. Maybe the correlation was a statistical artifact of the detection setup. These were not silly objections. They were real gaps in the experiment. Alain Aspect, a French physicist, decided to close them. Working in Paris in the late 1970s and early 1980s, Aspect redesigned the Bell test with one crucial improvement. He changed the measurement settings randomly during the flight of the photons, after they had already been emitted. This meant the photons could not carry advanced knowledge of what was going to be measured. It closed what physicists called the locality loophole. His results, published in 1982, violated Bell's inequality again. More decisively this time. The correlations were real. They were not an artifact of the detectors or the setup, but there were still loopholes. And so the experiments continued, decade by decade, each one closing another gap. Better detectors, longer distances, faster switching, each experiment tightening the constraints on any alternative to quantum mechanics, and each one produced the same answer. The world is not the way Einstein needed it to be. The test still was not finished, but the direction was clear, and one more experiment would close the remaining doors. In 2015, a physicist named Ronald Hansen and his team at Delft University of Technology in the Netherlands ran what is now considered the first loophole-free Bell test. Let me tell you what they did. They placed two entangled electrons 1.3 kilometers apart in separate buildings on the Delft campus. Each electron was entangled with a photon. and those photons were sent to a central station where they were measured together, creating entanglement between the electrons without the electrons ever having been in the same place. Then they measured the electrons' spins, quickly enough and far enough apart that no signal travelling at the speed of light could carry information from one measurement to the other before both were complete. The two measurements were, in the language of physics, space-like separated, completely causally disconnected, and the correlation still violated Bell's inequality. 1.3 kilometers. No shared signal possible. The major experimental loopholes had been closed. The result was published in Nature in October 2015. The experiment had for the first time ruled out local hidden variable theories without leaving any of the standard experimental gaps that a skeptic could point to. Einstein's picture of a locally real universe, where particles carry definite properties through space, had been ruled out under the standard assumptions of the experiment. A class of philosophical loopholes like superdeterminism remain technically on the table, but most physicists regard them as more costly to accept than the strangeness they're trying to avoid. The correlations between those entangled electrons, 1.3 kilometers apart, cannot be explained by any ordinary local hidden variable picture. Whatever quantum mechanics is doing, it is not something that fits into the classical story of objects carrying their properties with them through space. 7 years later, the physics community made it official. In October 2022, the Royal Swedish Academy of Sciences awarded the Nobel Prize in Physics to 3 scientists: Alain Aspect, John Clauser, and Anton Zeilinger. The citation read, "For experiments with entangled photons, establishing the violation of Bell inequalities, and pioneering quantum information science." I want to be careful about what that means, because it is easy to read a Nobel Prize announcement and think it is about technology, about quantum computers and encryption and the future of communications, and those things are genuinely in the citation, but the foundational reason this work earned the prize is something older and quieter. For 50 years, the experiments of Clauser, Aspect, Zeilinger, Hansen, and dozens of others had been systematically dismantling the possibility that reality, at the quantum level, works the way common sense suggests it does. The prize was, in a deep sense, a confirmation. Physics had officially established that the strange correlations quantum mechanics predicts are real, that local hidden variables do not exist, that the universe, at its smallest scales, does something that no purely classical picture can explain. Anton Zeilinger, the third laureate, had gone further than Bell tests alone. Working in Vienna and Innsbruck from the 1990s onward, Zeilinger's group demonstrated quantum teleportation, the transfer of a quantum state from one particle to another across a distance, using entanglement as the channel. Not the transfer of matter, not the transfer of a signal faster than light. The transfer of a quantum state itself, with the original state destroyed in the process to satisfy the laws of physics. Let me say that more carefully, because quantum teleportation is one of the most misunderstood results in modern physics. Imagine you have a qubit in an unknown quantum state. You want to send that exact state to someone far away without knowing what it is. You cannot measure it, because measurement would destroy the superposition. You cannot simply copy it, because quantum mechanics forbids perfect copying of an unknown state. This is called the no-cloning theorem. What Zeilinger's team showed is that you can use a pair of entangled particles as a channel. The sender performs a joint measurement on their qubit and one half of the entangled pair. This measurement destroys the original quantum state, but produces a classical result, 2 ordinary bits of information. The sender transmits those 2 bits to the receiver by any ordinary means: a phone call, an email, a radio signal. The receiver uses those 2 bits to perform a simple operation on their half of the entangled pair, And the result is that the receiver's particle now has exactly the quantum state the sender started with. No faster than light communication. The classical bits still have to travel the ordinary way, but the quantum state, the exact superposition, has been transferred. The original is gone. The copy, faithful to every quantum detail, exists somewhere else. Zeilinger's group teleported the quantum state of a photon across the Danube River in 2004. They demonstrated entanglement-based quantum key distribution over 144 kilometers between two Canary Islands in 2007. These were not demonstrations that the physics was exotic. They were demonstrations that the physics was real enough to be engineered. Eva Olsson, a member of the Nobel Committee for Physics, said during the announcement that the laureate's work had opened doors to another world and had shaken the very foundations of how we interpret measurements. Shaken the foundations of how we interpret measurements. This is not modest language. This is the Nobel Committee saying, in careful scientific phrasing, that what happens when you observe a quantum system is still genuinely not understood. Not a matter of missing details, a foundational open question. And then, 2 years later, a machine named Willow walked into that open question and made it harder to ignore. If you're finding this interesting so far, now is a good time to hit like, or subscribe if you have not already. It really does make a difference for a channel like this. Now, back to it. On December 9th, 2024, Google Quantum AI published a paper in the journal Nature announcing their new quantum processor Willow. Willow has 105 qubits. Its coherence time, the window before environmental interactions destroy the quantum state, is around 100 microseconds, about 5 times longer than Google's previous processor, Sycamore. And in a benchmark test designed to show what quantum computers can do that classical computers cannot, Willow performed a calculation that Google's team estimated would take the fastest classical supercomputer on Earth, a machine called Frontier, approximately 10 septillion years to complete. Let me give that number some scale. 10 septillion years is written as a 1 followed by 25 zeros. The current age of the universe is about 13.8 billion years. Times 10 septillion years is roughly 700 trillion times longer than the universe has existed so far. Willow completed the equivalent calculation in about 5 minutes. Now, to be precise about what this means, the benchmark task, called random circuit sampling, is not a real-world problem. It doesn't cure diseases or crack encryption. It is deliberately constructed computation that quantum computers are good at, and classical computers are catastrophically bad at. The comparison is meaningful as a demonstration of computational power, but it does not mean Willow will solve practical problems at this scale anytime soon. Researchers are clear-eyed about the distance still to be travelled before quantum computers become routinely useful. What the benchmark demonstrates is something else. The quantum computer is doing something. There are qubits in superposition, entangled with each other across the chip, computing across an enormous space of possibilities simultaneously. The statistical pattern that emerges matches the quantum prediction in ways no classical machine could feasibly reproduce. The engineering works, the quantum mechanics is real. Here is something else worth knowing about Willow. As Google scaled up the number of qubits and increased the chip size, something happened that had never been demonstrated before. The error rates went down. In classical computers, more components usually means more places for things to go wrong. In Willow, as the number of qubits grew from a 3x3 grid to a 5x5 to a 7x7, the error rate dropped by a factor of 2 at each step. This is called below-threshold quantum error correction. Physicists had predicted it would be possible in theory for decades. Willow showed it was possible in practice. It is one of the key milestones on the road to a fault-tolerant quantum computer, a machine that could run long enough and cleanly enough to solve real-world problems that no classical machine could approach. The machine is not finished, but it is moving in the direction physics said was possible. And Hartmut Neven, the founder of Google Quantum AI, said something in an interview after the announcement that sparked a debate far larger than the benchmark number. Neven said that Willow's performance lends credence to the notion that quantum computation occurs in many parallel universes, in line with the idea that we live in a multiverse. The benchmark does not distinguish between interpretations, it does not prove many worlds. What it does is make the old interpretive question feel harder to ignore. If the machine is doing something that no classical computer could replicate across all of cosmic time, the question of where that computation is happening becomes less abstract, less philosophical, more urgent. Neven was not making this up. He was invoking a specific interpretation of quantum mechanics called the many worlds interpretation, developed by the physicist Hugh Everett in 1957. Here is the core idea. The Schrödinger equation is smooth and continuous. It never breaks down. It never calls for a collapse. It just keeps evolving the quantum state forward in time. But when you measure a qubit, you get a single definite outcome, one answer. The Copenhagen interpretation handles this by adding a measurement rule. The wave function updates to reflect the observed outcome. Many physicists treat this as a practical rule without committing to what it means physically. Hugh Everett said, "What if there is no collapse at all? What if the Schrödinger equation just keeps running? What if, when you measure a qubit and get 0, there is also a version of the universe where you got 1? And those two versions simply stop being able to interact with each other because they have become entangled with different environments. In the many worlds picture, every quantum measurement branches reality. Every possible outcome happens in a separate branch. There is no collapse. There is only an ever-expanding tree of branches, each one containing observers who see one consistent set of outcomes. And Neven's point was this. If quantum computers are genuinely exploring an enormous space of possibilities simultaneously, and doing so in ways that no classical computer could replicate, even given all the time in the universe, then where is that computation happening? If all you have is one physical chip in one physical lab, where are the other branches of the calculation? Many worlds says in other branches of reality. The quantum computer is in some sense computing in parallel across many worlds at once. David Deutsch, one of the pioneers of quantum computing theory, made a similar argument decades ago. He said the power of quantum computation is, in his view, most naturally explained by many worlds, now. It is important to be clear about what this is and what it is not. This is one interpretation, a serious one, taken seriously by a significant number of physicists. But it is not the consensus. There is no consensus on the interpretation of quantum mechanics. There are several competing pictures, and all of them match every experimental result we have ever collected. The experiments cannot, as of today, distinguish between them. The many worlds interpretation is not a fringe idea, but saying Willow proves it would be going far beyond what the physics actually shows. What Willow shows is that quantum mechanics works at scale. The math is real, the computation is real, and the interpretation of what is happening underneath remains genuinely open. Every door you try to open out of the strangeness leads somewhere else that is strange. Here is where the situation actually stands. Physicists have several competing interpretations of quantum mechanics, yet all of them reproduce the same experimental predictions. None of them has been ruled out by experiment, and each one requires you to accept something deeply uncomfortable about the nature of reality. The Copenhagen interpretation is the one most physicists learned in school and most textbooks teach. In this view, the wave function is a calculation tool. It tells you the probabilities of measurement outcomes. In many textbook versions, collapse is treated as a rule for updating the state after measurement, not necessarily a physical event happening somewhere in space-time. Before measurement, probabilities. After measurement, one observed outcome. The discomfort, What counts as a measurement is not precisely defined in the theory. The boundary between quantum and classical is fuzzy, and the transition from many probabilities to one outcome has no equation in the fundamental law. It is simply a rule appended to the theory, practical and predictive, but philosophically unfinished. The many worlds interpretation, as I described a moment ago, removes the measurement update entirely. The wave function never gets updated. Every outcome happens in a branching universe. You, as an observer, happen to find yourself in one branch. The other you, in the other branch, got the other outcome. The discomfort, the number of branches grows astronomically with every quantum event. There are, in this picture, an almost incomprehensibly large number of copies of you branching at every moment. The branches cannot communicate. There's no way to verify they exist. Some physicists find this picture elegant. Others find it extravagant beyond reason. The pilot wave interpretation, developed by David Bohm in 1952 and rooted in earlier work by Louis de Broglie, takes a different approach entirely. In this view, particles always have definite positions. There's no superposition of the particle itself. Instead, there is a real wave, a pilot wave, that guides the particle's motion. The wave can pass through both slits in a double-slit experiment. The particle goes through one, but the wave's interference pattern determines where the particle ends up. This restores something Einstein would have appreciated. Particles are real. They have definite states. But the pilot wave interpretation has its own price. The wave that guides the particle is non-local. It can instantly respond to things happening far away. The connection between entangled particles is built into the structure of the wave itself. Local realism is still gone. The non-locality is just made explicit rather than left mysterious. The discomfort, a wave that influences particles faster than light, even if it cannot be used to send information, feels like a violation of something fundamental. There are other views. Relational quantum mechanics, developed by the physicist Carlo Rovelli in the 1990s, proposes that quantum states are not absolute but defined relative to other systems. There's no single objective state of a particle. Different observers, interacting with the same system at different times, have consistent but not identical descriptions. Reality, in this picture, is a web of relationships rather than a collection of objects with fixed properties. Cubism, developed by Christopher Fuchs and colleagues, goes further. In this view, the wave function does not describe the world at all. It describes an agent's beliefs and expectations. Measurement updates beliefs, not reality. The quantum world in cubism is not directly accessible to any description. All we ever have is our expectations and their outcomes. Let me bring Schrödinger's cat back briefly, because it is the clearest way to see how these interpretations actually differ in practice. Copenhagen says, "The cat's fate is determined when the measurement happens, when the quantum event at the radioactive atom level is amplified into a definite record somewhere in the system. Before that definite record exists, the question of whether the cat is alive or dead is not meaningful. The cat is not in superposition in any physically real sense. The question simply does not have an answer yet. Many World says, both outcomes happen. There is a branch of the universe where the cat is alive and a branch where it is dead. The observer who opens the box finds themselves in one branch. The other observer, in the other branch, finds the other outcome. Both are equally real. There is no collapse, only branching. Pilot wave says, the cat is definitely alive or definitely dead before you open the box. The wave function guided the radioactive nucleus through a definite trajectory, and the outcome was determined. Your ignorance of the outcome is ordinary classical ignorance, like not knowing which side a coin landed on before you look. The strangeness is in the wave, not the particle. Relational says, whether the cat is alive or dead is only defined relative to a system that has interacted with it. Before the observer opens the box, the cat's state relative to the observer is undefined. After opening, it is defined. Different observers, interacting with the system at different points, may have different but consistent accounts. These are not the same claim, they are genuinely different pictures of what is going on. And as of today, no experiment has cleanly distinguished between the major interpretations. They all work, they all fit the data, and each one asks something strange of us. You're lying in a room right now, your hands are resting somewhere, on a blanket, on your chest, on the mattress beside you. The atoms of your hands are following quantum mechanical laws at every moment. Their electrons exist in quantum states. Their behavior is governed by the same equations that govern those qubits cooling to 20 millikelvin in Santa Barbara. The only reason your hands feel solid and definite and perfectly classical is that they are constantly, relentlessly, interacting with everything around them. Every photon of thermal radiation, every air molecule, every contact with the mattress. The environment has been entangling with your hands continuously for every moment since before you were born, and the result of all that entanglement at the macroscopic scale is a classical hand with classical properties. You are classical because the environment never stops finding out about you. For most of the 20th century, physicists had a phrase for handling the interpretation problem: shut up and calculate. It is usually attributed to David Mermin, though he later said he intended it as a description of a bad attitude rather than a prescription for one. The phrase captured something real about the culture. Quantum mechanics worked, its predictions were astonishing, and debating what it meant was something you did on Friday afternoons if you had spare time. Quantum computers changed that. Here is why. When quantum mechanics was purely a theoretical framework, or a tool for understanding atomic spectra and particle collisions, you could, if you wanted, treat the wave function as a calculation device. A convenient fiction that gave right answers without necessarily describing anything real. Many working physicists did exactly this, without it affecting their work at all. But when you build a machine, you're making a commitment, a physical, engineering commitment to the idea that the mathematics describe something real enough to be worked with. Consider what the engineers who built Willow actually had to do. They had to cool 105 qubits to 20 millikelvin because they understood that decoherence is a physical process. Whatever the wave function represents, it is disrupted by uncontrolled interactions with the environment, and that disruption is real enough to ruin a computation. They had to build a chip where qubits could be entangled with each other, because entanglement is real enough to be engineered. They had to develop error correction protocols that protect quantum information across multiple physical qubits, because superposition is real enough that its fragility matters at scale. Whatever the wave function represents, the quantum state it describes has to be physically protected. The superposition is not a convenient fiction. It is a real condition that can be created, manipulated, and destroyed. And so when the machine runs a calculation that no classical computer could complete in any humanly meaningful time frame, and the statistical output matches the quantum prediction, something happened. The qubits did something. Whatever is described by the wave function, in that machine, in that calculation, it was real enough to do it. And that is the shift quantum computers represent. For 80 years, the interpretation of quantum mechanics was optional. The math worked regardless of what you believed the math described. Quantum computers have made the interpretation matter in a new way, not because any interpretation has been proved, but because we are now building real machines with real engineering requirements on a foundation whose nature we do not fully agree on. That is an unusual place for mature technology to stand. We are building factories on a foundation that we understand with perfect precision and understand not at all simultaneously. The measurement problem is not a new question. It was identified in the earliest days of quantum mechanics. Werner Heisenberg, Niels Bohr, Erwin Schrödinger, Paul Dirac, all of them wrestled with it. Schrödinger invented his famous cat thought experiment precisely to show how absurd things became when measurement language was applied to everyday objects. Here is the setup. Imagine a cat sealed in a box with a tiny piece of radioactive material. The radioactive material has a 50% chance of emitting a particle within 1 hour. If it does, a detector triggers a mechanism that releases a poison, and the cat dies. If it does not, the cat lives. Now. According to quantum mechanics, before you open the box and look, the radioactive particle is in a superposition of decayed and not decayed. It has not chosen. It is both, mathematically speaking, until something records which it is. If the radioactive particle's state is a superposition, then the detector linked to it is also in a superposition of triggered and not triggered, and the mechanism is in a superposition of released and not released, and the cat, following the same logic, is in a superposition of alive and dead. Schrödinger did not believe this. He thought it was a reduction to absurdity. The quantum mechanics of the 1930s, he was saying, cannot possibly mean that a cat is both alive and dead until someone opens the box. Something must happen to produce definite outcomes before we look. But the theory, as written, it did not specify what. That was 1935. The cat is still in the box, in a manner of speaking. Decoherence has helped. The theory of decoherence, developed seriously in the 1970s and refined over subsequent decades, shows mathematically why large objects become classical. The physicist Dieter Zeh in 1970, and later Wojciech Zurek at Los Alamos in the 1980s and 90s, worked out how quantum superpositions become practically undetectable once a system is large enough. Constant interaction with the environment scrambles the phase relationships of superpositions so rapidly that they become unobservable. A grain of dust in ordinary air decoheres in roughly 10 to the minus 31st seconds, far too fast for any instrument to catch. Zurek introduced a concept he called pointer states to explain this more precisely. When a quantum system interacts with its environment, not all superpositions are equally fragile. The ones that survive, the ones that the environment keeps selecting and amplifying, are the ones that correspond to the classical properties we actually observe. Position, energy, momentum. The environment acts like a filter, constantly measuring the quantum system in certain ways and ignoring others. The properties that survive that filtering are the ones that become classical reality. Zurek called this process quantum Darwinism. The quantum states that get copied into the environment, that leave records in multiple places, are the ones that become observable. The ones that do not leave records decohere into invisibility. What we call objective classical reality is, in this picture, the small set of quantum information that the environment has selected, copied and amplified into the world around us. It is a beautiful and strange idea, and it explains a great deal about where the classical world comes from, but it does not fully solve the measurement problem at its core. Here is what decoherence explains. It explains why you never see a cat in superposition. The cat is far too large. It interacts with far too many particles. Its quantum superpositions decohere in time so short they are essentially instantaneous at any scale we can measure. The cat is classical before you open the box, before you even reach for the latch. Here is what decoherence does not explain. Why, when the cat's fate was decided at the quantum level, one outcome happened and not the other. Decoherence tells you the quantum coherence leaks out into the environment, but in the many worlds picture, it leaks out into all the branches. In the Copenhagen picture, it collapses to one, and decoherence cannot tell you which picture is right. It cannot explain why one branch is experienced rather than another, or what selecting one outcome rather than a mixture of outcomes actually means. The measurement problem is still open. Decoherence moved the furniture, but did not close the door. Quantum computers have made the measurement problem more urgent because they have made it more practical. We are building industries, laying the foundations of future technologies, investing billions of dollars on the basis of a theory whose foundations are not agreed upon. That is not a crisis. The engineering works regardless of the interpretation. But it is a remarkable situation. And the closer engineers get to making quantum computers useful, the more clearly that gap stands out. I want to return to something from the beginning of this. The machine has to be cooled to 20 millikelvin, colder than the void between galaxies, not because the engineers want it that way, because without that isolation, the environment keeps interacting with the qubits, and those interactions keep destroying the quantum state before the computation is done. There is something worth sitting with in that image. The universe is not a passive background in which events happen. It is an active participant. Every particle, every photon, every vibration of the air is constantly interacting with everything around it. The universe is, in a sense, constantly entangling with itself. And the result of all that entanglement at the scales we live on is the classical world we experience. Solid, definite, local, causal. But underneath that world at every level, the quantum rules are still running. Your hand, lying there in the dark, is made of atoms, whose electrons are described by wave functions. Those wave functions are being continuously disrupted and re-entangled by interactions with the environment. The result, statistically, is a classical hand with classical properties. But the quantum substrate is always there. The strange rules did not switch off when the universe got big enough for chemistry and biology. They scaled up, and the strangeness averaged out into the enormous number of particles involved, and the classical world emerged from that average. But the foundation is quantum, all the way down. When a quantum computer isolates a qubit at 20 millikelvin and holds its superposition for 100 microseconds, it is not doing something exotic and alien. It is doing something very ordinary, in very controlled conditions. It is holding a quantum state away from environmental interactions long enough to be useful. For a tenth of a millisecond, the machine is holding open a door that the environment normally keeps firmly shut. And through that door, we get a glimpse of something that has always been there, underneath everything. Underneath the blanket you're lying under, the air in the room, the slow rhythm of your breathing. The atoms of your body right now are following quantum rules. Their electrons are in quantum states. The photons of thermal radiation washing through the room are quantum particles. Every interaction between them is, at the fundamental level, a quantum event. You do not experience any of this as quantum because the sheer scale of the interactions, the trillions upon trillions of particles constantly entangling and re-entangling, produces the smooth classical picture your senses are built to read. The world is quantum. It has always been quantum. We just live on the classical surface of it, where the environmental entanglement has already happened and the possibilities have already resolved into the familiar, and the strangeness is pressed just below the level of everything you can touch. Here is what quantum computers have actually exposed. Not a flaw in physics, not a mistake in our understanding, something older and stranger than that. They have exposed the fact that the question we thought we could set aside, the question of what reality does when nobody's looking, is not a question that stays set aside. It is active, it is urgent, and it is now, for the first time, an engineering problem. We were not wrong about quantum mechanics. Quantum mechanics is the most precisely tested theory in science. We were incomplete in our understanding of what it describes, and the incompleteness has been there all along, sitting patiently in the mathematics, waiting for us to build something that made it impossible to ignore. The measurement problem is not going to be resolved by building faster computers or more sensitive detectors alone. It is a question about the nature of reality itself. about whether the wave function is a real thing, or a tool, or a description of many worlds, or a guide for invisible particles, or a statement of beliefs. And every answer on the table asks something strange of us. The next time you reach out your hand in a dark room, feeling for something familiar, the atoms of your fingers are following quantum rules at every moment. Their electrons are in quantum states. Their interactions with the air and the surface you're reaching for are, at the smallest scale, quantum events. The environment is constantly entangling with your hand and resolving its quantum possibilities into the classical solid object you feel. You're the classical surface of a quantum world. And somewhere in a laboratory in California, there is a chip cooled to a temperature that does not naturally exist anywhere in the universe, holding that surface open for 100 microseconds at a time, asking the question that physics has been unable to fully answer for a century. What is really happening underneath? Then the double-slit experiment asked it first in the 1920s. Einstein and Bohr argued over it for 30 years. Bell turned it into a test. Clauser, Aspect, and Zeilinger spent their careers running that test. Hansen ran it without loopholes in 2015. The Nobel Committee acknowledged it in 2022. And Willow, in December 2024, made it feel like the question is not going to let us be comfortable again. There is a particular kind of quietness that comes with sitting inside a question that does not have an answer. Not the frustration of a puzzle with a missing piece. More like looking at the night sky and realizing that the darkness between the stars is not absence. It is space that is genuinely there, real and vast, and you are inside it. The strangeness of quantum mechanics is not something that happens in laboratories to specially prepared particles. It is the operating system of the universe. The rules that make your body work, that keep the electrons in your atoms from collapsing into the nucleus, that determine how proteins fold and how photons carry light across a room, those are quantum rules. Your existence is a quantum computation that has been running for billions of years, maintained by the constant interaction of your atoms with the environment around them. The only difference between you and a qubit is scale. You're too large, too warm, too entangled with everything around you to exist in a detectable superposition. The environment has resolved your quantum possibilities into classical facts long before any measurement could catch them. You are the outcome. The branch, the answer that the universe selected. But the mechanism by which that selection happened, the physics of how one definite classical world emerges from the quantum fog of possibilities, is still written in chalk on a board somewhere, unfinished. Nobody knows the full answer yet, but the asking is now a machine, and that is not nothing. Sleep well. If you made it to the end of this one, thank you. It means a lot. If you found it worth your time, a like or a subscribe is the best way to let me know, and it helps more people find videos like this. Rest well tonight.